Swayam Prabha. Digital India. Educated India.
So, welcome to the second lecture of the module on rolling element bearing. In this lecture, we will study about the selection design methodology. That means how to choose the best rolling element bearing for our application or for a particular application. This is basically a selection design methodology where from the manufacturer's catalog we choose the best bearing, and so it is called the selection design. So, first of all we will study different steps in the selection methodology, and then one example problem will be solved. The selection of bearing type in a particular application depends upon the requirement of the application and the characteristics of different types of bearing. That for low and medium radial loads we go for ball bearings. For heavy loads and large shaft diameters we go for roller bearings. Deep groove ball bearings, angular contact bearings and spherical roller bearings are used in the applications where the load acting on the bearing consists of two components, that means the radial force and a thrust load. Self-aligning ball bearings and spherical roller bearings are used in applications where a misalignment between the axes of the shaft and housing is likely to exist. Thrust ball bearings are used for medium thrust loads. For heavy thrust loads, cylindrical roller thrust bearings are recommended. Double acting thrust bearings can carry the thrust load in either direction. For high speed applications, deep groove ball bearings, angular contact bearings and cylindrical roller bearings are recommended. For high rigidity, double row cylindrical roller bearings or taper roller bearings like examples of the machine tool spindles are used. In the low noise applications where we want very low noise, then we go for deep groove ball bearings, for example household applications. Now, the next important thing is the static load capacity of a bearing. That means under static load condition, how much load a bearing can sustain. Now, we know that in the rolling element bearing we have inner race, we have outer race, and in between the inner and outer race rolling elements are there, and the shaft will apply load, either the radial load or the thrust load, through inner race to the balls and it will be transmitted to the outer race. Now, static load is defined as the load acting on bearing when the shaft is stationary. It produces permanent deformation in balls and races. So, the ball is given, it produces the maximum load carrying capacity. Under that condition, permanent deformation in balls and races are produced, which increases with increasing load. Now, the permissible static load, that means the amount of maximum static load that can be applied, will depend on the permissible magnitude of the permanent deformation. That means what amount of permanent deformation can be allowed under static load condition, that will govern what will be the maximum load carrying capacity. So what happens is, if a load is applied, then these balls carry those loads, and the heavily loaded ball is this one, the P1, because it comes directly under the radial load, and other rolling elements share the load, and the amount of load carried by rolling elements decreases when you move in this direction and in this direction. From past experience, it has been found that a total permanent deformation of 0.0001 of the ball and roller diameter. It means if ball and roller diameter is d, then 0.0001 times diameter deformation occurs at the heavily stressed ball and race contact, and that can be tolerated in practice without any disturbance like noise or vibration. Because you see, this is the race curve, and you have a ball here. Then initially there will be a point contact in the case of ball, and in the case of roller there will be a line contact. Now, under static load condition, if some deformation has taken place in the ball, then this point contact will become a surface contact, and due to that, when this ball will rotate, there will be lot of noise and vibration. So without having crossing the limit of permissible value of noise and vibration, this 0.0001 times diameter of either ball or roller deformation is allowable. Okay, so it says that a total permanent deformation of 0.0001 of the ball or roller diameter occurring at the most heavily stressed ball and race contact can be tolerated in practice without any disturbance like noise and vibration. The static load capacity of a bearing is defined as the static load which corresponds to a total permanent deformation of balls and races at the most heavily stressed point of contact equal to this maximum permissible value, 0.0001 times the ball or the roller diameter. So we have seen that this is the surface of the inner race, and a ball is here, and along this the radial load W is acting. So this ball will be the heavily stressed ball in comparison to the other balls or the rollers. So the static load carrying capacity of a bearing is defined as the static load. Let that static load is represented by C and some subscript which we will see. This amount of load is applied, and a total permanent deformation of balls and races at the most heavily stressed point of contact, this is the most heavily stressed point of contact, is equal to, here the deformation delta is 0.001 times diameter of either ball or the roller. Then the load which is producing this deformation is called static load carrying capacity of the bearing. The values of static load carrying capacities are directly given in the manufacturer's catalogs, which are based on above formulae, where conditions of friction, noise, smoothness are not critical. A much higher permanent deformation can be tolerated, and consequently static loads up to 4 times the static load carrying capacity may be permissible. On the other hand, where extreme smoothness of operation is desired, a smaller permanent deformation is permitted. The basic static load rating, it is given in C0. So, this is the static load carrying capacity. So, on the heavily stressed point of contact, this is the ball or roller, this is the heavily stressed point of contact. The load which you are applying is C0, and this C0 load is producing permanent deformation equal to 0.0001 times diameter of the ball or the roller. Well, this C0 is the load carrying capacity. So, the basic static load rating C0 is defined in ISO 76 as the load that results in a certain value of contact stress at the center of contact of the most heavily loaded rolling element oblique raceway. The contact stress values are because this is the point of contact, and we know that at the point of contact stresses or the Hertzian stresses acts. So, the maximum value recommended by this ISO 76 is 4600 megapascal for self-aligning ball bearings, 4200 megapascal for all other ball bearings, 4000 megapascal for all roller bearings. These stress values produce a permanent deformation of the rolling element and raceway that is approximately 0.0001 of the rolling element diameter. Well, so when you are applying this C0 static load which is producing deformation equal to 0.001 times diameter, 0.0001 d, the diameter of the roller or bearing, then the amount of contact stress that is permissible or that is produced is this one for the self-aligning, this one for the ball bearing, and this one for the roller bearings. The loads are purely radial for radial bearings and axial centrically acting for thrust bearings. This load C0 is purely radial for the case of ball bearing or for the case of radial bearings, and it is purely thrust type or acting along the axis of rotation in the case of thrust bearing. The C0 is acting in this way for the thrust bearing, and it is acting in this way for the case of radial bearing. Now, let us find a value of load that acts on the heavily stressed ball, and that is called the Strybeck's equation. The assumptions which are taken in this mathematical modeling is the races are rigid and retain their circular shape. That means the inner race and outer race are rigid. There will not be any deformation in the inner race and outer race. Whatever deformation will be, it will be in the rolling elements, either ball or the roller. Now, the second assumption is the balls are equally spaced. The spacing between the balls are same, equally spaced balls are there. The balls in the upper half do not support any load. That means the balls which are on the upper half of the bearing, that means the ball here, then in this direction a ball which is here, in this direction another ball, then we have a ball at this location and at this location, this and this. it is said that the balls on the upper half, is this ball, these balls, will not participate in the load carrying. If load is acting in a downward direction, then the balls which are at the lower half of the bearing will carry the load or support the load. Now, what happens is, due to this C0 load, C0 is the static load capacity, the maximum amount of load, static load that can be applied, and that will create some permanent deformation, a small amount of permanent deformation at the heavily stressed point of contact. Then let the deformation in the heavily stressed ball is delta 1 and on adjacent ball is delta 2. So, this deformation is delta 1, this is delta 2 and delta 3. The deformation in the heavily stressed ball 1 is delta 1. On the adjacent two balls 2 and 2 dash, the deformation in the ball is delta 2 and it is clear that delta 1 will be greater than delta 2. Similarly, adjacent to the ball 2 are ball 3 and 3 dash, and the deformation in ball 3 and 3 dash is delta 3, and it is again clear that delta 2 will be greater than delta 3, because 1 is the heavily stressed load and it is directly coming under the load. Then, as there is no deformation in the races, and so due to deformation in the ball, the races will move from its center O to center O dash, so that this deformation, this displacement is equal to your this one. Okay. Now, the forces which are acting on the downward balls are P1, P2, P3, and the static load which is acting on the bearing is C0. So, you can find the component of forces in the vertical direction and the downward direction C0 by applying summation of all forces in the vertical direction is equal to 0. And as the loads are symmetrical, these reactions are symmetrical, their horizontal component will support each other or nullify each other. So, there will be summation of force, vertical forces equal to 0, and by this way you will relate the forces which are acting or the reactions which are acting at the balls with the static load carrying capacity C0. So, that is shown here. C0 is equal to P1 plus 2P2 cos beta, where beta is the angle between the two balls, and this will be same because the balls are equally spaced. So, the angle by which they are separated are beta and beta. So, the C0 is P1 plus 2P2 cos beta plus 2P3 cos 2 beta. As the races are rigid, only balls are deformed. Suppose delta 1 is the deformation at the most heavily stressed point of contact, or the heavily stressed ball, which is ball number 1. Due to this deformation, the inner race is deflected with respect to the outer race through delta 1. This is delta 1. Suppose delta 1, delta 2 and delta 3 so on are radial deflections at the respective balls. Okay, the radial deflections, earlier it were there and it has deflected like this. So, delta 2 will be given by delta 1 cos beta, and so delta 2 divided by delta 1 will be cos beta. Now, according to Hertz equation, that means Hertzian contact stress, the relationship between load and deflection at each ball is given by delta is proportional to load which is acting on it to the power 2 by 3. And also delta 2 is equal to delta 1 cos beta, and so we have delta 2 divided by delta 1 is cos beta, and delta is proportional to p to the power 2 by 3. Therefore, delta 1 is equal to, this proportionality is converted into equality by having a constant of proportionality equal to C1. So, delta 1 is C1 P1 to the power 2 by 3, where P1 is the force which is acting at the first ball. This is the P1 and this is the first ball, and here P2 and P2 and P2 are acting on the second ball. Okay, so and delta 2 is equal to C1 P2 to the power 2 by 3. So, delta 2 divided by delta 1 will be P2 divided by P1 to the power 2 by 3. From equation B and C, we will have P2 divided by P1, this P2 divided by D1 is equal to this delta 2 divided by delta 1, which is equal to cos beta. So, P2 divided by P1 to the power 2 by 3 will equal to cos beta, or P2, the force acting on the second ball, is equal to P1, the force acting on the first ball, and cos beta, this is the beta angle, to the power 3 by 2. In a similar way, we can find other forces acting on the other balls. That means on the third ball, this third ball, the force P3 will equal to P1 to cos 2 beta to the power 3 by 2. Substituting these values in equation A, that means this equation where C0 is equal to P1 plus 2 P2 cos beta plus 2 P3 cos 2 beta. So, substituting the values of P2, P3 and others in terms of P1, we got C0 is equal to this formula, and taking common P1, we have within the bracket 1 plus 2 cos beta to the power 5 by 2 plus 2 cos 2 beta to the power 5 by 2, and like that. Now, the term within the bracket is taken as m, is called m. So, C0 is equal to P1 multiplied by m, where m is the term within the bracket. Now, if Z is the number of balls, then beta will be 360 divided by number of balls. The values of m for different values of Z are tabulated as follows. For Z is equal to 8, 10, 12, 15, m is equal to 1.84, 2.28, 2.75, 3.45, and so Z divided by m will be this one. Now, we know we have found this C0 in terms of P1m, and beta is this one. So, we will have a relation between m and Z. So, it is seen from the above table that Z divided by m is practically constant, 3.45, 4.38, 4.36, 4.37. So, Strybeck suggested the value of Z divided by m equal to 5. So, m is equal to 1 by 5 multiplied by Z, number of balls or the number of rollers. Okay. So, substituting this m in this equation of C0, C0 is equal to P1 multiplied by m, and now m is 1 by 5 Z, and so C0 is 1 divided by 5 Z multiplied by P1. From experimental evidence, it is found that the force P1 required to produce a given permanent deformation of the ball is given by K, a constant, and D square, where D is the diameter of the ball, and the factor K depends upon the radii of curvature at the point of contact and on the modulus of elasticity of the materials of the ball and the races. From equation F and G, we have C0 is given by Kd square Z divided by 5. This gives the static load carrying capacity of the bearing, and that is also called the Strybeck equation. Now, the rated life. The bearings are designed and made for some life. The manufacturer gives a life of a bearing. That life is called the rated life. This may be different from manufacturers to manufacturer. So, to get a particular type of rated life, a person may refer the catalog of a manufacturer, but in general it is given as the fatigue life of a bearing, because on the bearing the load which is acting is variable type of load, because we saw that the heavily stressed load is just below the radial load. So, when that ball after rolling goes to the upper half, then the load reduces and then becomes 0. Then again it comes near to the line of action of the radial load, then load on the ball increases, it becomes maximum, and then again it starts reducing and will become 0 when the ball will move along the upper half of the bearing. So, the load is a fatigue load. So, the life of the bearing is limited by the fatigue failure at the surfaces of balls and races. The rating life of a group of apparently identical ball bearings, apparently identical bearing. That means the life is not determined for a particular ball bearing. A group of identical bearings. Okay, we have taken n number of bearings, bearing number 1, 2, 3 to n, and all are identical, same type of bearings. Now, a particular load will be applied on them, all of them, same amount of load, and they will be allowed to run at certain RPM. Okay, and then all will be observed for first evidence of fatigue crack. Well, then the rating life of this group of identical bearings is defined as the number of revolution or cycles that 90% of the bearings will complete or exceed before the first evidence of fatigue crack. The meaning is, when all these bearings have run up to n number of cycles, then it has been found that 10% of the bearing have failed. Failed means they have, in all those 10% of bearings, fatigue crack has started. Fatigue crack has started. And 90% of the bearings in this n number of bearings are safe. In that, the crack has not initiated. The crack has initiated only on 10% of the bearings. So 10% of the bearing will be said to have failed. So this revolution n till 90% of the bearings are safe is called the rated life of the bearing. Well, there is a number of terms used for this rating life. They are minimum life and or the catalog life and represented by L10. L10 means 10% of the bearing has failed and 90% is safe. For the majority of bearings, the actual life is considerably more than the rated life because we have taken n number of cycles and we are taking the rating life where 10% have failed, but rest 90% is safe. So it may be found that for a particular bearing, the number of revolution till first evidence of fatigue crack will be more than this rated life. But as fatigue is statistical in nature, and so this rated life is taken for selection of the bearings. The next is the dynamic load capacity. The dynamic load capacity of a bearing is defined as the radial load in the radial bearing. So in the case of radial load, radial bearings, radial load is applied, or thrust load in the thrust bearing. Thrust load in the thrust bearings that can be carried for a minimum life of 1 million revolutions. Most of the manufacturers of rolling element bearings take rated life as 1 million revolutions. Okay. So dynamic load capacity of a bearing is defined as the radial load in the radial bearings or thrust load in the thrust bearings that can be carried for a minimum life of 1 million revolution or the rated life. The meaning of that is you have let a bearing like this, that in between is the balls, and the rated life is let 1 million revolutions or 10 to the power 6 cycles of revolution. And therefore, when we were studying the rated life, then we said that to determine the rated life, n number of a group of identical bearings are taken and a particular load is applied. A particular load is applied and the bearing is allowed to run at particular RPM. Then the number of revolutions till 90% of the bearings are safe or 10% of the bearings have failed, and the fail means evidence of fatigue crack or the initiation of crack. So let this NP, the number of cycles or the revolution, is the rated life or 10 to the power 6 number of cycles. So what you will do is you will apply a load in such a way that those n number of identical bearings are run at a particular RPM, then up to 10 to the power 6 number of cycles, only 10% of the bearing has failed. Only 10% of the bearing has failed. Then this load is called the dynamic load capacity. The minimum life in this definition is the L10 life, which 90% of the bearings will reach or exceed before fatigue failure. Dynamic capacity is represented by a letter C or C10 also, C or C10. C0 was for the static load capacity and C10 is for the dynamic load capacity. So either C or C10 is used to represent the dynamic load capacity. The dynamic load carrying capacity is based on the assumption that the inner race is rotating while the outer race is stationary. The formulae for calculating the dynamic load capacity for different types of bearings are given in the standards. However, the manufacturer's catalogs give ready-made values of dynamic load capacities of bearings. Now, the dynamic load capacity was given as the radial load in the radial bearing and thrust load in the thrust bearing. But the force acting on bearing has two components, radial and thrust, and a combination may also be there. So there may be a combination of radial load and axial load, but the dynamic load carrying capacity, dynamic load rating is given for radial load in the case of radial bearing and axial load in the case of axial bearing. But if a combination of load is there, then what to do? So it is necessary to convert the two components acting on the bearing into a hypothetical radial load fulfilling the conditions applied to the dynamic load carrying capacity. So what we do is, if both radial and axial load is acting on a bearing, then this axial and radial load is converted into a hypothetical radial load, and that is called the equivalent bearing load. Equivalent bearing load. Then the hypothetical load can be compared with the dynamic load capacity. Now, equivalent dynamic load is defined as the constant radial load in radial bearings, which if applied to the bearing would give same life as that with the bearing will attain under actual condition of forces. The meaning is, we have a condition where both radial load Fr and axial load A is acting. So we will convert it into an equivalent load, which is either called the Fe or simply P as given in this equation, P. So this P is actually a hypothetical radial load. Hypothetical radial load. So it is assumed that when this equivalent load or this P will act, then it will produce the same effect on the bearing if this Fr and Fa will act. Okay. So the equivalent load P or equivalent load Fe is given as X V Fr plus Y Fa, where P or Fe is the equivalent dynamic load in Newton, Fr is the radial load which is acting on the bearing, Fa is the axial or thrust load which is acting on the bearing, V is the race rotation factor. It depends on whether the inner race is rotating or the outer race is rotating, and X and Y are radial and thrust factors respectively, and their values are given in the manufacturer's catalog. Now, let us see how this equation has been derived and what is the genesis of this equation. When a ball bearings carry both an axial and thrust loads Fa and a radial load Fr, an equivalent radial load Fe, that does the same damage is used. A plot of Fe divided by VFR, Fe divided by VFR versus Fa axial load divided by race factor V and Fr is obtained experimentally, and the experimental data are shown by small circles. These are the experimental data. So from the experimental data, it is clear that up to certain value of Fa divided by VFR, the value of Fe divided by VFR is almost constant, and its value is equal to 1. Well, and after certain value of Fa upon VFR, the relationship between Fe divided by VFR and Fa divided by VFR is linear, where this V is a rotation factor to account for the difference in ball rotations for outer ring rotation versus inner ring rotation, and V is given as 1 for inner ring rotation and V is equal to 1.2 for outer ring rotation. So if outer ring is rotating, we will take this V as 1.2, otherwise it will be 1. So this differentiating point where the data point is almost constant up to the value of 1, and after that where there is a linear relationship, this is called E. So we may see that when Fa divided by VFR is less than or equal to E, then your value of Fe divided by VFR is equal to 1. Well, and beyond that there is a linear relationship, and that linear relationship can be obtained by the intercept of this best fit line. This is the best fit line. This one is the best fit line of the experimental data. When this line is extended, then it intersects the y-axis at point x when Fe divided by VFR is equal to x, and the slope of this line is given by y. So we can find the equation of this line. So we can relate the Fe divided by VFR with Fa divided by VFR when E is when your Fa divided by VFR is more than E, and that is given in this table. The x and y for specific bearing obtained from bearing catalog is shown in this table, which gives representative values in a manner common to many catalogs. That means, first of all, we have to find what is the value of E in this curve. We were having Fa divided by VFR, and here we have Fe divided by Fe divided by VFR. Well, and the relationship was something like this, a linear, and this point was E. Okay, and the intercept was x and the slope was y. So our first aim is to determine the value of E, and that E is given for a ratio FA divided by C0. Okay, FA divided by C0 gives us certain values. So let you have a bearing, and that bearing has the value of C0. So get the ratio, the axial force divided by C0, and correspondingly the value of E is there. And then after getting E, now you have two values depending on the value of FA upon VFR less than or equal to E, whether you are in this zone or you are in this zone. So if you are in this zone, you will refer this one to get the value of X and Y. Now if you are in this zone where the relation is linear, the condition is FA upon VFR is more than E. FA upon VFR is more than E. Then these two columns will give you the value of X and Y. So what you have to do is, you have to simply first determine the value of FA upon C0. That will give you the value of E. Depending on the value of E, you will compare either this or this to get the value of X and Y. Now knowing the X and Y, you will get the equivalent dynamic load, selecting the value of B depending on whether the inner race is rotating or the outer race is rotating. So you will get X VFR plus Y FA. Now equivalent load you have. Now the next thing that we are going to study is the relationship between load and life. The nominally identical groups of bearings are tested to the life failure criteria at different loads. A plot of load and life on log-log scale is approximately linear. The experimental data are given as a small circles between log of the load which you can apply on the bearing and log of the life. Okay, and we have studied what the meaning of this life is for the case of bearings. So it has been found that with the increase in load, the life decreases. With decrease in load, life increases on the log-log scale. This is a log-log scale. So by drawing a best fit line, this is the best fit line. The regression equation gives the relationship between the load and the life, and that is F multiplied by L to the power 1 upon A is equal to constant, where A is 3 for the ball bearings and A is equal to 10 by 3 for roller bearings and cylindrical and tapered roller. Now applying that equation to the two load life conditions, that means this is the log of the life and this is log of the load, and the curve is like this, and we want to apply it for two conditions, the condition number 1 and condition number 2. So there will be first life and second life, F1, F2 and L1, L2. So the relationship will be F1 multiplied by L1 to the power 1 by A is equal to F2 multiplied by L2 to the power 1 by A. Now denoting condition 1 as rated catalog rating, this one is taken as the catalog rated which we get from the catalog. So we will say the first as FR LR to the power 1 by A is equal to the desired value. This is called the desired. So, catalog is giving the rated load and rated life, and we want this load is to be applied on our bearing, and we want this life. So, the relationship will be just like this. Now, the unit of L are revolutions. Life is revolution, number of cycles. If life L is given in hours at a given speed n in RPM, applying a conversion of 60 minutes per hour, this L will be given by 60 times Ln. This L is life in hours. So you can write this equation as 60 life in hours and RPM. So revolution life is given in hours life. Now solving equation A for FR, which is just another notation for the catalog load rating, C10 is equal to FR, the rated load. Rated load will be given by this C10 is equal to FD, the desired load which you want to apply, the desired life and the rated life to the power 1 by A. Now, if this L is converted into this hour life, then this FD in place of LD we will have within the bracket, in place of LD we will have 60 LH desired and RPM N desired divided by 60 L rated multiplied by number of RPM rated to the power 1 by A. So, with this we are ending this lecture, the lecture number 2. In this lecture number 2, we studied the way the life and load are related, and before that we studied the static load rating and the dynamic load rating and the rated life of the bearings as per the catalog. Thank you.
Hello, I am A.K. Sharma and I teach sociology in IIT Kanpur. I am attempting to answer a simple question, what is sociology? Now friends, one simple answer would be that sociology is a study of human behavior. And this study of human behavior has a history. Actually, due to growth of science, technology and due to industrialization and economic development in the West, initially there was a hope that by application of science and technology, the face of this world can be changed to the advantage of mankind. But what was found or what was observed, that this did not happen. And despite economic development, urbanization, industrialization, surveys showed that poverty had increased, unemployment had increased, even health conditions became worse. And today you will be surprised to know that there was a time when death rate of urban areas was higher than the death rate of rural areas. Cities or the places of development, industrialization and education and enlightenment became consumers of rural population. So people started asking, why is it so? And some philosophers, engineers, mathematicians who contributed to emergence of a discipline like sociology started thinking that perhaps we need a new subject in which we will apply the same tools and techniques which are being used by scientists, mathematicians, physicists, chemists, but we will study human behavior. In other words, we will try to discover if there are laws of human behavior, and by applying those laws perhaps in the future the condition of mankind can be improved. This is how sociology developed. Initially Auguste Comte called this social physics. He also used terms like social statics and social dynamics, the usual division of mathematics, and he believed that social statics will study relationship between different parts of society and social dynamics will study relationship between parts of society and total society, change in total society. Now, you may ask that if sociology is the study of human behavior, there are many other branches of social sciences which study human behavior, economics, anthropology, psychology, etc., etc. The difference between sociology and these disciplines is that while in these disciplines we study one specific aspect of human behavior, like economics will study production and distribution of wealth, psychology will study cognitive processes or mental models or personality, social psychology will study personality, anthropology will study culture. Now, somebody has to relate one aspect of human behavior with the other aspects or one social fact with the other. These are all social facts for us. And if somebody tries to link cognitive processes with economic conditions or urbanization or caste system or religion, or somebody tries to relate urbanization with human psyche, or somebody tries to correlate cultural context with economic behavior, then it becomes sociology. So, sociology combines different areas which are individually studied by different disciplines. And sociology also studies new questions which are not studied by any existing subject so far. So, like these days issues of waste disposal, entropy, environment, safety, urban places as new geomorphological systems come up, and we want to correlate one aspect of urbanization, say percentage of population living in urban areas, and risk, environmental risk, carbon dioxide, this emission, that emission. Now, which will be the first discipline to take interest in these things? Because sociology. So, sociology not only combines facts from different aspects of society, sociology also addresses new questions. And I can also say that one central feature of sociology is to explain individual behavior or individual psyche in terms of properties of larger society. In simple terms, if you imagine that there are two aspects of human behavior, individual and society, then while other disciplines like psychology are focusing more on individual, we study characteristics of individuals in terms of certain characteristics of larger society. This is what sociology does. Sociology is very useful for planners. Sociology is useful for answering new questions, as I said, which have not been answered by any existing discipline. And I would say that sociology is especially helpful for self enlightenment, because sociology only tells you that there are no right of social issues, it is not physics. not have fixed answers to issues, because questions from variety of perspectives. So, role of stress, power, etc. also come up in answering social questions, and it is this aspect from variety of perspective, that something can be looked at from the perspective, can be looked at entirely differently from the perspective of people, NGOs, or from the perspective of experts. This real to self enlightenment and empathy. Thank you.